we have studied different types of trees till now, right? Again, I will explain. We have seen about the binary trees first, then we went to binary tree, then we went to binary search tree, right? Then we have seen AVL trees, and also we have seen heap trees. Okay. The other version of tree what we have after this is B tree. Again, this is not a sequence, it is not one upon other, it is not one upon other. This heap is different. AVL and these are in a chain. Okay, if I draw the exact diagram of how this chain looks like, on this we have AVL trees, but from binary tree we have something called heap trees. From here we have something called B tree. Okay, from binary tree itself, or I can even say from trees concept we have B tree or binary trees. Binary tree, what is rule of binary tree, right? Binary tree strictly says that it can have either one node or two nodes or zero nodes as its children. Okay. Binary search tree we are imposing some logic, again some more logic, again a different type here. In trees we have a different type called B trees. Okay. So, if you remember, initially when we studied trees concept, we did not say that a node should have only one element. We were studying something like this. It can have multiple child, it can have only one child, this can have two children. All these are trees. These are all trees. When I said binary, I said only two children, like this, or two or one, something like this. When I said binary search tree, some rule was there in the data part, but the tree structure was looking binary only. Even in BST and in AVL tree structure was still a binary logic only, right? Same thing, heap means again a binary tree only, because everything can have only two elements like this. And even heap is a full complete binary tree. It is a complete binary tree. Heap is a complete binary tree. Okay. Then we have something called trees. So, from this original base tree, we are studying about B trees. What is B tree here? B tree again, actually the concept of tree plus balancing factor. Okay, where did you study balancing factor? We studied balancing factor in balanced binary search tree, or that is also called as AVL tree. We were talking about balancing factor. The height of the left child, and the right child should differ by 1, right? In the concept of this AVL tree, we said that. So, a normal tree with multiple elements like this, there is no limit. No, in tree we do not say there is any limit. I can have n number of childrens like this. Okay. But having, you have to maintain a balancing factor along with the tree. So, this is a normal tree structure. Okay. In that you have to maintain the balance, the height of left and right you have to maintain. If that you are able to maintain, that is called a B tree. Again, this is just an overview understanding of what is B tree. If someone asks you what is difference between binary tree and B tree, you can say this, right? Here it is strictly two children, but here it is multiple children. But there are some conditions again, here again. Okay, it is also kind of binary tree, right? So, what is B tree? How does it looks like? See, first node will have only one element, second node will have two elements each. Here there will be one key, only 10. Here I will have something called 15 and 25. Here I will have two elements 45, 55. So, this is having only one element inside that node. This is having two elements, this is having two elements. Then its child, how many, for this one, how many children are there? 2. For this one, there will be 3 children. So, I have a node like this, where I will be having 3 elements, 1, 2, 3, some 4, 5, 6, 7, 8, like this. Okay. Now, how many children will this have? This will have 4 children. Okay. This will also have 4 children, right? So, if you observe, first node is having 2 children, second level are having 3 children, third level nodes are having 4 children. Okay. This is the concept of B tree. Let us go deeper into the understanding of binary tree, B tree, right? When it comes to storing and searching large amount of data, binary search tree is little impractical. Why? binary search tree, if I give some elements 10, 15, 12, 15, 19 or 16, something like this, right, you are following some order like this, your tree becomes very large. If you have more elements, no, it becomes very difficult like this. Again, this is growing in terms of complexity. See, it is growing in terms of complexity. Okay, this is binary search tree, but in B tree I can store multiple elements. No, here I am having two elements, here is one, here I am having three, here also three, here also three elements. So here 3, here 3 and here 3. See, level 1 1 element, level 2 4 elements, here 9 plus 9 18 elements. So total how many elements? 18 plus 4 plus 1, it is 23. To store 23, the maximum height of the tree is 3. 1, 2 and 3 levels, only 3 levels are there. Whereas here to store 23, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So the height is 1, 2, 3, 4, 5. The height of the tree is increasing 5. Whereas in B tree it is only 3. So we are having a small height tree. So traversing, playing operations on a small height tree is very easy. Number of iterations are less, right? That is what it is said here. So when it comes to storing and searching large amounts of data, traditional binary search tree can be impractical due to its poor performance and high memory usage. Okay. B tree are also known as B tree or balanced tree, are a type of self-balancing trees that was specifically designed to overcome these limitations. Which limitations? Poor performance and high memory usage of a binary search tree, right? Unlike traditional binary search trees, B trees are characterized by the large number of keys that they can store in a single node. Okay, in the implementation of tree or binary search tree, we were using linked list, no, like this, the element 10 here, the left pointer and the right pointer. Here also same thing, the element 20 here, left pointer, right pointer. Here also same thing. See how much memory I need? I need lot of memory, because I am creating block, I am increasing the size of the tree. But in B tree, in a single node, I can have multiple values. I can have 3, 7, 9. This is left key, this is right key. Okay, this way I can have. That is what it is saying. Unlike in traditional binary search trees, B trees are characterized by large number of keys that they can store in a single node. In a single node, I can store many number of 3, 7 and 9, all 3 I can store, which is why they are known as large key trees. B tree are also known as large key trees. Okay, where are they useful? See, B trees are particularly useful for storage systems that have slow bulky data access. If I implement binary BST logic, tree structure becomes very big to store data points. So when the tree structure is very huge, you see how many traversals I have to do. Okay, if you see this example, you have to do so many traversals, right? If you want to find out a node, suppose this is my tree, assume if I want to find out some element, I have to start here, then go here, this side, I have to keep doing it. When the level is small, it is only very small steps. Within very small steps, you will get the you will find the element. Okay. So when you have large data and where you have a storage system that have slow bulky data access, such as hard disk, floppy and CD-ROMs, we use this B trees. Okay, you are going to study about this B tree widely in the concept of DBMS, database management systems. Okay, or advanced DBMS, you have this concept of B tree. We will see that application of B tree, right? B tree maintains balance, which guarantees that time complexity is very less, that is order of log n. Searching is same as your BST. In binary search tree, searching is order of log n only. Here also it is order of log n, right? But the number of levels or the height of the tree is reducing. That is the advantage of this B trees, right? So this is an example. See how does a B tree looks like. If you see here, I have one key. Here there are 2 keys each, and here there are 2, 2, 3, 2, 2, 3. The logic is that the root node, okay, the root node should have less than or equal to number of nodes in their children compared to their children. So here there are 2. So root node should be less, or I can say the children of a node can have less than greater than or equal to number of nodes. If this root is having one key, its children can have 1 or greater than 1, that is 2. It can have 1 or 2. So 2, 2. Now this node is having 2 children, 2 elements. So their children, this node's children can have either 2 or 3 children. Okay, so like this. Now what about this node? How many children will this node have? It will have 4. It can have 3 or it can have 4. It can have 3 or it can have 4 nodes. Okay, that is the just an example to demonstrate how B tree looks like. Okay, this is the keys. Key means the element which I am going to store. So if a root node will definitely contain one element. Its children can contain, this left child can contain 1 or 2 number of keys. Here also 1 or 2. So we are having 2, 2. So their children can contain 2 or 3, like this. It goes on. And another thing, if you observe, all the elements are in every node. In every node, this is very, very important observation. In every node, the elements are in sorted order. See here, in this 100 only, so no need of sorting. Here you see 35, 65. Here you see 30, 130, 180 in sorted order. Here 10, 20, here 40, 50, 70, 80, 90, everything in sorted order. All the keys, all the elements in a node should be in sorted order. Okay, that is very important. They should be in sorted order. Next, another observation you see, when you have 100 here, when you are having 100 here, its left child will contain elements less than 100, right child will contain element greater than 100. This is your logic of BST, right? Left child will contain elements less than 100, right child will contain elements greater than 100. That is one more important thing. Next, when you have two elements like this, 35 and 65, right? The leftmost child of 35 will be less than 35, the rightmost child of this will be greater than 65, and the middle elements will be in between 35 and 45. See this here, see the observation here. See, left of 35 are 10, 20, which are lesser than 35. Right of 65 are 70, 80, 90, which are greater than 65. And the middle element, you see, the middle element contains the element between 35 and 65, that is 40 and 50. That's why B tree is very, it has many benefits. Why? It is nicely sorted. We are storing elements into B tree in a sorted order. Searching some element is very, very quick. Okay. Why? Because tree is nicely framed. It is also satisfying BST logic. It's also satisfying BST logic, and in each node elements are in sorted order. That's why searching is very easy in B tree, and the advantage is height is very less. The height of the tree, same elements if you want to store in BST, the height will be very high. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. To store 19 elements, height will be 5 definitely in BST, but here it is only 3. 1, 2 and 3, right. So this is about B tree. Let's understand little some properties about B tree. All leaves are at same level. All the leaf nodes are at same level. Next, B tree is defined by the term minimum degree T. Okay, T, we will talk about this T. What is the minimum degree? Every node except the root must contain at least T minus 1 keys. At least T minus 1 keys. The root may contain minimum of 1 key, that is fixed. All nodes may contain at most 2T minus 1 keys. See, if this is having, if here T is equal to 1, they can have 2 and 2. That's what we are saying, no? See, they can have 2T minus 1. What is 2T minus 1? They can have at most 2T minus 1 keys, right? When T value is 2, 2 means 2 into 2 minus 1, that is 3, 4. See, at most they can have 3 elements. This is having 3, this is 2, this is 2, this is 3, this is 2, 2. So when T value is 2, you can have at most 3 elements, right. Next, number of children of a node is equal to the number of key in it plus 1. How many children does a node have? So how many children does this node have? This node you see, How many keys are there? 2 keys are there, 35, 65. 2 plus 1. So it has 3 children. You take this. How many keys are there here? There is 1 key. Plus 1. It has 2 children. Right? That is another property. All keys of a node are sorted in increasing order. See, every element is in increasing order. Next, the children between two keys K1, K2 contains all keys within the range from K1 to K2. Here, see this. The children between 35 and 65, this one, this link contains the element between K1 and K2. This is your K1 and this is your K2, including K1, K2 are kept here in the middle node. Right. Insertion of a node in B tree happens at only leaf node. We can insert an element only at the leaf node. Right. Suppose if you want to insert, for example, I want to insert 45, I will be inserting 45 here. Okay. Now, if I want to insert 15, I can insert here. Suppose I want to insert 25, I can move 20 here and insert 25 here. We will sort it. Suppose you want to insert maybe what else, 35, if I want to insert 38, then we will be inserting, we will be moving this 38 here and 40 like this. Now, if you want to insert 42, already there are 3 elements, 38, 40, 50 is there. You want to insert 42, right? Then you will have to split it and insert it. Okay. So, this is some properties of B trees. Some simple interesting facts, again these are all based on the number game. So, minimum height of a balanced tree that can exist with the n number of nodes, and m is the maximum number of children of a node can have, right. The minimum height of a B tree that can exist with the n number of nodes and m is the maximum number of children a node can have is h is equal to log n plus 1, that is in this example if number of nodes, right. So, if you count the number of nodes 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So, it is 9 plus 1, 10 minus 1. M is the maximum number of children of a node can have. What is the maximum node a children can have? It is M. That is here it can have maximum 3 like this. That gives you the height. It is again somewhere, if you see 3 square 9, no. So, you get the height of the tree as the 3. Same way, the maximum height of a B tree that can exist with n number of nodes and t is the minimum number of children, then this is the equation. Okay. These are again you can anyhow you need not remember this. If some questions are there, you can answer them by seeing by drawing a B tree. Okay. Formulas you need not remember them. Traversal, how do you traverse in a binary in B trees? Same like we do in binary tree in order traversal. Always left, then root, then right. See, leftmost child, recursively print the leftmost child, repeat the same process for the remaining children. Okay. Then at the end recursively print the rightmost children, right. How do we do recursion here? First these 2, right, then this children, then this one, again this one and this one, you have to go in this order, right. You can print them in the same order of in order traversal. Search operation, let us see an example. Let us try to understand how we are increasing the speed of searching an element using B tree. Okay. How we are trying to increase the speed of an element in B tree, right. So, see, I said here this one K1, K2, right. The child between 2 keys K1 and K2 contains all keys in the range from K1 and K2. This example, 35 is your K1, 65 is your K2. This side I know it will be less than 35. This side everything will be less than 35. This side everything will be greater than 65. What about middle elements? They will be within this range of K1 and K2. That is the point here. Contains all keys in the range from K1 and K2. Okay. So, search operation, let us see how to search. So, I have a B tree with me like this. I want to search an element 120. So, what will happen? The first step is it will check the root element. Is this root element equal to 120? Is it equal to? No. Then check, is this root element less than 120? Yes. Then move towards right hand side. That is what we are doing in BST, no? In BST what we do? You check the root. Is it equal to the element? No. Is it less than, go left child. Is it greater than, go right side. So same way here, since 120 is greater than 100, I will go to the right child. Again in right child I will come like this. Now you will check here, you will make a double condition. This is the element which I am searching for, right? The control comes to this node now, right? Then it will check in which range the key, is it greater than 100, okay, is it greater than 100 and less than 130, then go on to the left side, okay, or is it greater than 100 and greater than, next condition will be, is it greater than 130 and less than 180, go into this child. Then is it greater than 180, go in this child. Like this we will be going. So in this case what happened, the element is less than 130, so we will come in this node. Okay, we come to the left side of this node, left child of this 130. Next again you will compare with this 120 with this 110. Is this 120 less than 110? No. First you will check it whether it is equal or not. Then is it equal to less than 110? No. Then is it greater than 120? No. Then you, anyhow at the first check itself you are getting key is equal to 120, is matching. No, it is matching here directly. But if it is not matching, we will do that case. Is it less than, is it greater than, we will keep doing that, right. So like this we will search an element in a B tree. Okay. So searching is very easy because it is just going in 3 steps. We are finding that element 120 if it exists. If it does not exist, again it's programming to write. If the element does not exist, return -1 element not found. That's all programming part. But logically understanding search operation is just in 3 steps. Here you are checking, then here you are making a check, then here you are making a check. Okay, right. So what are the applications of B tree? Where do we use this B trees? It is used in large databases to access data. Okay, when you have large data, you have to maintain B tree. Why? B tree holds the linkage of which is the parent, which is the children. That linkage it is maintained in database. That's why you will understand this much better when you study DBMS concepts. Okay, then searching for data in the dataset can be achieved significantly in less time, easily achievable. Okay, with the indexing feature, multi-level indexing can be achieved. Multi-level indexing, right? Most of the servers use B tree approach to store the linkage. Again, it is used in CAD, it is in cryptography, NLP. Lot of applications are there for B trees. Advantages: complexity is order of log n. It is self-balancing. Why it is self-balancing? Every element we are putting in proper order. We are putting, you are using BST logic, and in each node you are sorting those elements in ascending order. So it is self-balancing. High concurrency and high throughput, fast edge. Efficient storage utilization. If the tree is very high, number of nodes required is very high, but the tree size is very small, it is easy to store. But what is the drawback here, right? B trees are based on disk based data structures. Okay, so they require high disk usage, meaning they are stored in the disks. Okay, hard disk, not best for all the cases. Slow in comparison with other data structures. BST is the best one, but for smaller size, right? You can apply B tree when more number of keys are there. Okay, so this is little about B tree, advantages and disadvantages. If you quickly see what is B tree, right? So B tree also stands for balanced tree or large key. Okay, we are maintaining multiple keys. In each node we are having multiple keys. The root will have 1, its children can have 1 or 2 here, and their children can have 2 or 3 elements in each node. Like this the tree is exist. Okay, so this is about B tree. It has wide applications in the database especially, but anyhow B tree has some drawbacks. Because of that we have come up with a new concept, that is the B plus tree. Little drawbacks of B tree are overcome in B plus tree, right? We will see this in our next video.